Very good evening. This is the last video of this week. Since last two lectures on DH parameters and DH representation, I thought I can make a short video where I can show how we can actually get the DH matrix or ARM matrix with the help of DH representation. And on the go, I will actually explain the DH parameter. So what are the DH parameter, how we can actually realize, so which is we call simply kinematic parameters in our manipulator course. So this is what we are going to call kinematic parameters. In the sense it would be having two subclasses. So one is what you call link parameters, the other one you call joint parameters. The link parameters are associated with you call xi minus 1, where the joint parameter is associated with zi. So this link parameter further it would come as actually like alpha I minus 1, where it is linked twist angle, and the other one is ai minus 1, which is what you call link length, and the other two are actually like the angle between two you call links, that is what you call theta I, which is nothing but joint angle. Then there is a offset between two planes, so that is what you call offset distance, right? These four parameters we can actually realize. So and then what we have seen, that DH representation would be having two form. So one is we call standard form. So one is we call standard form, the other one is non-standard. And in our course we are actually going to talk about non-standard. What that mean? So here actually we would do first the rotation about z, then the translation about, or you call translation about along z, then you do actually rotation about x, then translation along x. So this is what we used to do in the you call standard form. Okay, so this is standard form where the first operation is rotation about z, then translation along z, then rotation about x, and translation along x. Whereas the non-standard is slightly different, where initially we will rotate about x, so then translate along x, then rotate about z, then translate along z. Okay, this is what the major difference. So the non-standard coming, why? Because there are actually two frame we are actually using, in the sense the link parameter would be in I minus 1 frame and the joint parameter would be in I frame. Whereas in the standard form everything would be in I representation, but these all parameter would be in I, or you can say represented with respect to I, but all these things will be realized with the help of you call I minus 1 and you call I. That is what the idea. So now since there is a you call you can say the lecture delivered about DH representation, so I'll take one simple example on the board and then we can get it. For example, just to give an idea, I take three you can say square blocks. So this is the first block, and there is another block which is actually I can say, so this is connected like this. Okay, so now the second block is actually parallel, but what you can see, the second block I am just drawing in another color. Okay, so these two blocks are actually having one joint. So I'll just make it, this is one joint, and this joint is actually I just shows as a pin. Okay, so now the second link, this is a link k minus 2, and this is link k minus 1. So obviously there is a further end. So I am saying that the further end is actually, okay, I'll just show it. So the further end is actually like this. So in the sense the third body is actually going slightly a different way. So in the sense this is the third body. So the third body is like this. Okay, so now you can see that this link this I call link k. So now if I take a random link, so I've taken random link k minus 1. So this link k minus 1 is actually associated with k minus 2 and k, and you can see that as per the Danawit-Artenberg, so the Danawit-Artenberg representation, there are several assumptions. One assumption is actually like binary links. So all the links are binary links. So in the sense, you can see that this is one of the binary link. This link would be having two joints. So one joint is actually like you can say connected between link k and k minus 1. The other joint is actually like connecting you can say link k minus 2 and k minus 1. So now in order to get the Danawit-Artenberg in function, so further what we have actually like got it. So the second assumption is all the joints are actually like 1D of freedom joints. Okay, and the third assumption, fourth assumptions and all we will actually like see over the you can say course. So now you can see that this is what my interest. I just take a random link. So for that I'm actually like showing this way. So this is the random link which is actually like I call k minus 1. Okay, so I'm just showing it that. So this is one joint. Okay, and this is another joint. Okay, and what further you have seen this what you call, so this link is actually like can rotate freely about this, and this link is actually like freely rotate with respect to this axis. Okay, so in order to give a little more clarity, or for example to understand this Danawit-Artenberg, so what I'm actually like trying to show this, I'll actually like wrap this just to show it in a other way. It is easy for you to understand. So I am taking the black color as a block, and you can see that this is the after rotation, this is the you can see the position of the you call, so this is actually like you call the third body. Okay, the third body is actually like oriented like this. The first body you can say you can say oriented like this. Second body is actually like oriented like this. In the sense, so when I draw the frame diagram, you can see that the you call the third frame we call ith axis. Okay, so the ith axis where the xi is going like this. Okay, and now what we know as per the you call coordinate basis, and this is what the rotation. So the link k minus 1 is actually like rotate like this. So in the sense, this is link k minus 1 is actually like rotated like this. And what happened, this is the joint axis. Along or about this joint axis it can go translate like this to and fro, or it is rotated. So in the sense, if you see, this is the first joint axis which I call say I minus 1, and there is another joint which is actually like I'm showing it here as a green color. So this point, so this is I call ith frame, and this is actually like I minus 1 frame. Okay, so I think it's supposed to be I minus 1, you can take it so that it would be uniform. So now this joint axis is like this. Okay, so in the sense, this the third link is actually like rotated about this particular blue box. So now it is actually like can rotate like this or translate up and down. So in the sense, you can see that these are the frames which is associated. So just to give little more clarity, I am just showing in another figure, or probably I am just drawing it here just for giving little you can say insight. So this is what the Zi. Okay, so where xi is already defined. Okay, so this is the ith frame, and whereas the other one is what you call the other axis. So this is what the other axis which is actually going inside the iPad, and this is what I call I minus 1 frame. So what we wanted the information which is the transformation information of ith frame with respect to I minus 1. Okay, this is what our interest. So in the sense, this transformation matrix, can we get it? So in order to get that, what we can do, you can see that these are actually like you can see these are actually like having this, you can say rotation apart, distance apart, and your x-axis like this. So you have actually like several operations, and we said that the Danawit-Artenberg will do with 4 you can say transformations. That 4 transformations only we are trying to see here. Okay, So in the sense I am actually like showing the red one is actually like my I minus 1 frame, and in order to give clarity, okay, so in order to give clarity I am just showing you call this is what is at I minus 1, and in order to show clarity I am just showing it, this is a black color I, and this is what Z I. Okay, so now what we are actually like doing it, the first operation what we are actually like trying to do, we are trying to make it parallel. So in the sense the Z I minus 1 trying to make it parallel to Z I. So obviously these two are actually like distance apart, so definitely we cannot do it, and I am just showing this is what the xi, okay, just to give a clarity. So now what we are interested to see this. So for that what I am taking a, you can say, parallel line here. This is parallel to Zi, okay, and I am actually like drawing this parallel. So I am just drawing this is parallel to Zi, and now I am actually like drawing a common normal between, you can see, Zi minus 1 and Zi. So you can see that if I actually like draw a line, so this is normal to this and this is normal to this. So now this is the common normal. So why we are doing the common normal? Because I want to find out what is the xi minus 1. So this axis would be actually like perpendicular to the plane consist of Zi minus 1 and Zi. Okay, so in the sense what we can do, we can actually like try to see which plane this would be having. So you can see in that sense what plane it is having. So if you are assuming that this is actually like the plane, imaginary plane, where this is Zi parallel and this is Zi parallel and this is Zi minus 1. So this is the plane. So in the sense you can see that the xi can be come in or out, and we know like this is going to be defined the link length. In the sense you can see that this is the positive direction towards the ith frame, that is what your direction of xi. So I defined xi minus 1. Okay, so the xi minus 1 what we wanted, that we can see that is the normal between the plane which is consist of Zi and Zi minus 1. So the normal towards the, you can say, I minus 1 to I, that is what you can say the, you call the xi minus 1 axis. So now you can see that about this xi minus 1, what one can see, the Zi and Zi minus 1 are actually like this, you can say oriented apart or rotated apart. So now I am taking the right hand rule, the sense I am putting this thumb finger along, you can say, or about xi minus 1, and I am trying to rotate. So what is the axis of rotation here? So here the axis of rotation is actually like this is the positive rotation. So in the sense I am trying to rotate here. So in order to give little clear, I am just using the black color here. I get new, you can say, axis. This is I am going to call something like ZP, and now I am actually like going to get, this is actually like XP, and now I am getting a new frame called P frame. And you can ask where is the X? As per right hand rule, you can see that once you know two axes, the third axis easily you can get it. That's why I am actually like skipping. So now what operation we have done? We have actually like done rotate, or you can say rotation about xi minus 1. In the sense the angle I am calling this is alpha, and we are taking the reference as xi minus 1. So this is alpha I minus 1. So the first operation what I did, rotation about or along, about or along, whatever way you want to take, and rotation about x-axis alpha I minus 1. Okay, this is the first operation I have done. So now what I got it, the P and I minus 1 is actually like only one operation difference, or only one difference. It is actually like the Zi minus 1 and Zp are you can say rotated apart with the angle of alpha I minus 1. So now what you can see, this P and the I are actually like distance apart. When I see along xi or xp axis, you can see that is the common normal. That common normal, if I travel, what I will reach, I take a car and I reach to the highway, right? So in the sense I will hit here. So now I will get one thing. What I will get one thing, I'll get the x-axis parallel, I call that is xq. and I can see that there is a z-axis would be, I'm just moving this frame some distance, which is I call link length, that is ai minus 1, because I am traveling along, you can say xi minus 1 in the sense here along xp, but what the distance I am going to call as ai minus 1. So in the sense, now what I am going to get, there is a new coordinate frame called q, where zq xq are actually like parallel to your zp and xp, but it is actually like translated apart along xp. The distance what I called as ai minus 1. Now what I did a translation. So the translation operation I am calling as a d. So the translation along x, and the distance is actually like a minus 1. Okay, so this is what I did, the second operation. So now what you can see, one, the ith frame and q frame is actually like distance apart, and xi and xq are, you can say, oriented apart or rotated apart. So now I am trying to do the third operation. I am trying to draw a common, you can say, parallel line. In the sense, I am actually like trying to draw a parallel line to xi, and now you can see that I am taking a, you can say, zi as the rotation. So in the sense, I am taking a new frame called r. Okay, that r z axis is actually like parallel to zi, and it is actually like originate from q. So now this frame I am calling r. So now what I am trying to do, I am trying to rotate xq, and I actually like make it parallel along with or about or parallel to xi. So now I am calling that as a new axis. Got it? So that is what I am actually like going to call as xr. So now xr and xq are actually like only difference is the theta variation, and this theta is actually like what I am realizing from the zi, so it is called theta I. So now what operation I did a rotation operation about z axis, and the angle is theta I, and this is the operation I did. In the sense, r and q are actually like only difference is the orientation about the z axis. So now you can see that the ith frame and the r frame are actually like only one difference, which is the translation along z axis. So in the sense, the distance between these two are actually like di. I am doing that as the operation. That is what you can see. Why it is di? Because this is along zi axis. So this is about zi axis. This is along xi minus 1. This is about xi minus 1. So now you can actually like get a clarity. So these two are actually like defining the link parameter, in the sense the relation between two joints it is giving, and this particular these two variable, you can see that that is giving the relation between two links, so about the joint. So these are the four operations we have done, and what one can actually like see here. So you can see that this, what you call here the link parameter, where you are actually like making it this parallel, okay, and you are traveling. So these two are actually like about the link. So it is actually giving relation between this green and this blue, which is we call joints. And whereas the about the blue, you can see that the link k minus 1 and link k relation is getting. That's what it is called. This is link parameter and this is joint parameter. So now you got a clarity, I hope, right? So now we can do what are the operation we have done. The first operation we have done rotation about, you can say, xi minus 1 with an angle of alpha I minus 1. Then we have done the translation along x, that is actually like the distance is ai minus 1. Then we have rotated about zi, that is theta I, the rotation angle, then joint angle, and then translation along zi, that is what you call di. Okay, this is what your transformation matrix, so of I with respect to I minus 1. Okay, and you know individual matrix, this is a rotation matrix, so obviously this is x-axis rotation, so the other terms would be 0, and this is actually like cos alpha I minus 1, and this is sin alpha I minus 1, and these are actually like 0, 0, and this is sin alpha I minus 1, this is minus, and this is cos alpha I minus 1, and this is 1, 0, 0, 0, right? So similarly, the translation matrix, or you can see the dx would be like 1, 0, 0 and a I minus 1, because the translation happened only along x-axis. So then the rotation matrix is simply identity and there is no other vector term would be there, right? So this is the, you can say, link parameters, and there is a rotation about z-axis. So that is what you are coming with a joint. So since it is actually like rotation about z-axis, so that axis you will get all 0 terms except that, and these are the remaining terms. Now I am writing this is cos theta I, and this is minus sin theta I, and this is sin theta I, and this is cos theta I. Okay, so now we have come the last stage where the rotation matrix is identity because we have done with only translation operation, that too like along z, the distance is di, and that is what we are actually like getting it. So now you can see that the difference between you call the standard and non-standard is actually like very straightforward. These two matrices you actually like multiply, and you post multiply with this to this, then that is going to give a standard, you can say post multiply this with this, that will give the non-standard DH representation. You can say post multiply this with respect to this, then that would give the standard DH representation. Okay, so that is the basic difference you can get. So when you talk about standard, this become only I. When you talk about non-standard, this I minus 1 will appear. That's the only difference you can get it. I hope you got a clarity on this. So tomorrow anyhow we have a live session. You can please post your question there and we can discuss. I'll try to bring some demonstration tool and then we can definitely go little further. With that, I'm actually like closing this short video, and see you on tomorrow. Bye bye. Take care.